Hello everyone. This is going to be a video about exponential and logarithmic equations. So if you've been keeping up with the lessons so far, we've been learning about exponential and logarithmic functions and, talking about their graphs and talking about their domain and range and properties and things like that. And that's good, and that's all been functions and expressions. And what this section is going to do is look at equations where we want to solve for x. So x is involved somehow with something exponential or logarithmic, and we want to kind of extract x and find out what it equals. Okay, so let's go ahead and get started. Okay, so exponential and logarithmic equations. These are kind of two topics. If we wanted to, we could separate them into two sections, but I'm going to keep them in one section. And yeah, we'll just have kind of two different topics to talk about. So let's start with a definition. We need to define what is an exponential equation. So we're going to say an exponential equation is one in which the variable appears in an exponent. All right, so it's not just any equation that involves exponents. It's particularly an equation with exponents where the variable appears in an exponent, and the variable is usually going to be called x. So we want to talk about how to solve these, and there's going to be a couple of strategies, but we're going to start with simple ones. So for simple equations, we can solve by using the definition of log. Definition of logarithms and logarithmic functions. So I'll show you an example of what I mean. You remember in the previous videos when we were talking about logarithms, in previous sections, we've said that you can sort of convert back and forth between something involving exponents and something involving logs, and vice versa. So let's say we are told to solve for x, and we're given 2 to the x equals 7. This is an exponential equation because it's an equation in which the variable appears in an exponent. And we want to solve for x. What would the definition of log tell us? Well, by the definition of log, this means that log base 2 of 7 equals x. That's what I mean when I say we can use the definition of log. Basically converting this exponential equation to something involving a logarithm instead of an exponent. There's the base, 2. 2 was being raised to a power, so the base is 2. And it says log base 2 of 7 equals x. In fact, it just so happens that we just solved it, right? We just found the answer. The answer is log base 2 of 7. That is what x equals. Now, that's not something we can simplify by hand. It's like saying 2 to what power equals 7. Side note. How big is log base 2 of 7? Like, this equals some kind of number. Can we figure out approximately what it is? You know, I've done this kind of thing before where I say, like, we could look at powers of 2 and figure out, do any of them equal 7? Well, if we're using integer powers, none of them are going to equal 7 exactly. This is going to be 1, 2, 4, 8. Those are powers of 2. And 7 is somewhere in here, between 4 and 8. So log base 2 of 7 is between, what can we say? It's bigger than 2, smaller than 3. Because if I did a 3, like if I did a 3 here, 2 to the 3 is 8. That's too big. 2 to the 2 is 4. That's too small. So what I want is something that's almost 3. I'm just going to say it's between 2 and 3. Now, I put all of this off to the side as a side note. The actual answer that I put a box around is perfectly fine the way it is. If you ask me what's the answer to this question, it's log base 2 of 7, period. We're done. Coincidentally, I did find this as a decimal using a calculator to be approximately 2.8. But that's, if we're not using a calculator, then we would just leave it. Log base 2 of 7 is the exact answer. Let's see another one. Let's say we want to solve for x. And it could just say solve. If it just says solve, then it's implied that we're looking for x, because that's going to be the only variable. 3 to the x plus 2 equals 7. All right, so this time, the variable appears in an exponent, but there's also some other stuff going on. There's a plus 2 up there. What I would suggest is we can still convert this into something involving a log. I guess this time the base would be 3, because it's 3 to a power. Log base 3 of 7 equals that exponent, which is x plus 2. So this time it didn't exactly get us the answer of x. We have one more step to do. To solve for x, we want to subtract 2 from both sides. So we could say the answer is log base 3 of 7 minus 2. That's the value of x that we want. Side note, I think we can check this. Take this answer and put it into the original equation for x. So 3 raised to the answer we found plus 2. Does that equal 7? Here, I'm going to circle the part where I'm putting in the answer. I put that in for x. Well, we have a minus 2 and a plus 2, so this simplifies to 3 log base 3 of 7. Does that equal 7? And yes, that does equal 7, because remember we had that property of logarithms that says 3 to the log base 3 are going to cancel each other out, leave us with just 7. So yes, we just checked our answer and found that it does work. So the point is, if an exponential equation is simple enough, then you can just kind of convert it into terms of logs, and your answer will either be there immediately, or maybe you'll have to subtract something from both sides, but you'll get to the answer pretty quickly. I'm going to show you another strategy, because sometimes equations won't be so simple. Sometimes we want another way of thinking of it. So I'm going to show you a strategy that is a 3-step process for an exponential equation. We could start by isolate the exponential onto one side of the equation. That means if there's exponentials on the left and the right, you try to move some things around, rearrange, get the exponential part just onto one side. Sometimes you don't even have to do that step, but just in case. Step 2 is kind of the big one, and it's going to say take a logarithm in some base of both sides and simplify. I'm going to say for some base b. The actual base that you use is going to depend on the problem, which base looks convenient to use. And finally, step 3 is going to be solve for the variable. I mean, that's what we're trying to do. So I'll show you to demonstrate this. I actually want to demonstrate this three-step process by showing it to you on the two problems that we just did. So we're going to revisit the two examples, but we're going to use this process and see what it looks like. So for example, 2x equals 7. What would it look like in this strategy? Well, first we would isolate the exponential on one side. It already is on one side. The exponent only appears on the left. So step 1 is done. Step 2, take log base b of both sides and simplify for some base b. So it's up to us what base we use. I think in this problem I would probably use base 2 because that seems to be the base of the exponential. So let's try doing log base 2 of both sides. We did a log of both sides. It says and simplify. So the and simplify would mean this part, log base 2 of 2 to the x, does simplify to just x. And there you go, that's the answer. That's the answer we found above. So we kind of got there in a slightly different way, but thinking of the problem this way also works. By the way, when I did this, we did log base 2 of both sides. Technically, you're allowed to use any base you want, as long as you do it to both sides. So what if you looked at this and you said, here, I'll show you a slight variation on this. What if I decided to use another base? Like instead of doing log base 2 of both sides, what if I did log base 10 of both sides? Would that also work? Well, it will, but what's it going to look like? Important thing is same base on both sides. Could we still get the answer this way? Well, the log and the 2 to the x do not cancel each other out. This does not cancel out to just be x. But what I could use is I could use that law of logarithms that says the x can be moved out front, right? Get this? Now divide both sides by log 2, and you get log 7 over log 2. Now, is that the correct answer? Yes, it is. I'm going to say these two answers are equal. If we were in person right now, I would ask you, can you see why these two answers are equal? It's because of the change of base formula. Remember the change of base formula? We talked about it not too long ago. Yeah, the change of base formula actually looks a lot like this. So you could have different answers, or I should say you can have things that look like different answers, but in fact they are equal to each other. Now we could have just, I'm just going to be clear here, we could have just done this part of the problem that we did at first, right here in the box, could have just done this and say we're done with the problem, the end. But I just wanted to show you that if you use a different base, you'll get an answer that looks different, but it can still be equivalent. It's still 2.807 something. And it's good to know that because if you're ever, like, let's say you're doing practice problems from a textbook, and let's say the textbook has answers in the back. The answer in the back of the book might look like this, or it might look like this. Your answer might look like this or this. You know, you could get an answer that looks different from the back of the book, but it could still be correct because of the change of base formula, or because of some log property or something. I also want to show you, so we're thinking of this three-step strategy. I also want to show you how it looks on this problem, where we're trying to solve for x from here. And to show you that we can use any base, I don't know, do we want to use base 3? 3 does seem the most convenient here. Let's just use base 3. Log base 3 seems the most convenient. I'm doing log base 3 of the left-hand side, log base 3 of the right-hand side. Any base, as long as it's the same on both sides. We do that because then on the left side, this simplifies to x plus 2. And now we subtract 2 from both sides. We get the same answer that we got earlier, just by thinking of the problem a little bit differently. Still gets us the same answer. On my page, I actually did this. I'll show you this. Why not? Okay, so we did it. We solved the problem. We're done. But I'm just going to show you. What if you prefer a different base? Like, I actually think when you get these, you should use whichever base the problem looks like it has. Problem with base 2, use base 2. Problem with base 3, use base 3. But if you like base 10, or what if you like base E? You could do ln of both sides. Technically, there's nothing wrong with that. I did a logarithm of both sides. Just happens to be with base E. And that looks like ln. I could take the x plus 2 and move it out front. Maybe a little more work involved with this one. ln 7 over ln 3. I'm trying to get x by itself. I get ln 7 over ln 3 minus 2. And that is also equal to what we found already because of the change of base formula. All right, now the problems that we've looked at so far, I would call them relatively simple exponential equations. It's been like 3 to the x plus 2 equals 7, things like that. We're going to gradually get to more and more complicated ones. And when we get to more complicated ones, we might need some steps before log, before doing log of both sides. You know, when I wrote it as a 3-step process, so far we haven't really had to do step 1. So this is what I mean. We might need to do something for step 1. Example, let's say we want to solve 5e to the 4 minus 3x minus 4 equals 36. Let's do this together. All right, so before thinking of using logs in any capacity, like if you're going to do log of both sides, or if you're going to use the definition of log to rewrite the problem, before you do either of those things, I would do some steps. I would do some rearranging, some simplifying. See this minus 4? That minus 4 looks like it'd be real easy to just, let's add 4 to both sides, right? Let's just do something about that minus 4. Add it to both sides. Boom. Problem looks simpler already. And now I see a 5 and a 40, and I think to myself, let's just divide both sides by 5. So by adding something to both sides and then dividing something by both sides, we made the problem look a lot simpler. Now it looks like one of those simple exponential equations, like that 3 to the x plus 2 equals 7. We have e to the something equals 8. Now it's up to us. Do we want to do it the first way we talked about in this video, where we use the definition of log, or do we want to do it the second way, where we said we're going to take a log of both sides? And really, it's up to you. I think I'm going to use the definition of log to say that this means, or this is equivalent to, a logarithm with base e. So this is like saying ln of 8 equals 4 minus 3x. You can get to that line in two different ways. Either what I'm doing is I'm thinking this is exponential. If I want to translate it into terms of log, it would be a log with this base. Log base e is written as ln. What would go next to it would be 8. What would go on the other side would be the 4 minus 3x. Or you could look at this and say, I want to do a logarithm of both sides. The most convenient one to work with would be base e. So if you did ln of both sides, ln of the left-hand side, do a little simplifying, you're still going to get to the same line. From here, we can definitely solve for x, right? Now it's just a matter of algebra. ln 8 is just a number, 4 is just a number. We need to get x by itself. So let's see. Let's rearrange. Let's get maybe like minus 3x equals ln 8 minus 4, and then x equals negative 1/3 ln 8 minus 4. Can we simplify that anymore? I think we might be able to. Let's see what we can do. X equals negative 1/3 ln 8 plus 4/3. Okay, I distributed across the minus signs. The reason that I'm doing this is because I'm thinking, I know what 8 to the 1/3 is. Here, scratch work. Do you know what, like if we took this 1/3, let me just show you what I'm getting at here. If I took this 1/3 and I moved it inside, let's do that. X equals ln 8 to the negative 1/3. Do you know what 8 to the negative 1/3 is? As a little bit of scratch work here. I'm doing this because I think we can simplify it. I wouldn't just move in any random fraction and combine it with any random number, but I'm combining this in particular because I think we can do it by hand. Well, this would be 1 over 8 to the 1/3. That's the same as saying the cube root of 8. And cube root of 8 is 2. So we could say this is ln of 1/2 plus 4/3. I think that looks a little simpler than what we had a couple of steps earlier. Or I think another way to write this that would still be a nice way to write this would be minus ln of 2 plus 4/3. I think either one of those looks good. So can you see that those two answers are equal to each other? That's the sort of thing where if you were doing a problem, well, for example, if you were doing a problem on a test, like I would have to watch out for this. I would have to accept both of these answers because they're the same thing. If you were doing a practice problem and you had some solutions that you could refer to, you should understand that these are the same. So if you get one of these answers and the answer says it's this other thing, they're exactly the same. I do think that this is a nice step to do when you have something like 8 to the 1/3. Just like if if we had a problem where I asked you, if you had a problem with like the square root of 16, I would expect you to simplify the square root of 16. It is 4. However, if you had a problem where the answer involved the square root of 17, I would say just leave it. Just leave it. Square root of 17 is not going to simplify any further. So it all depends on what you get. So that problem, if you look at how it originally was phrased, 5e to the 4 minus 3x minus 4, we did some little arithmetic first, algebra. Add 4 to both sides. Divide 5 from both sides. It's not so bad. I'm going to say we need to use what we know from algebra. I feel like when I say in classes, when I say we need to use what we know from algebra, I think that usually means factoring. Factoring is one of the important skills from algebra. So let me show you a different kind of exponential equation that we want to solve. This is going to be x squared e to the x plus x e to the x minus 2e to the x equals 0. Now, what can we do here? There's e to the x's. I'm thinking maybe like ln might cancel some things out. But I don't want to do ln of both sides here. I mean, there's a couple of reasons why I wouldn't do that. Ln of 0 is undefined, so that's not going to help us. And you can't just take ln of like each piece. Taking ln of a side would mean taking ln of like this whole object, not each piece. So what do we do here? What do we do? I'm going to say that I notice that each piece of this has e to the x. So we could factor e to the x out. And then see what this gets us. So really, this problem is like e to the x times a polynomial. And it happens to be a polynomial that can factor further. X squared plus x minus 2. This factors to x plus 2, x minus 1. Now, because the right-hand side is 0, look what we've got here. We've got something times something times something equals 0. All right, so that means that either e to the x is 0, or x plus 2 is 0, or x minus 1 is 0. Maybe we're getting multiple solutions here. Kind of solving this in a different way. It looks like we don't really need logarithms for this one. So this is sending me on 3 different paths. Maybe each one's going to get us a solution. Let's do the easy ones first. The easy ones. This is x equals negative 2. This is x equals 1. I'm going to say those are the easy ones. I'm going to put a box around it too. That and that. What about this though? E to the x equals 0. What is x going to be? It turns out that this never happens. There is no value of x that will ever make e to the x equals 0. And I'll tell you 2 ways that you can see that. One way is, in order to isolate x to get it by itself, you might do ln of both sides, but ln of 0 is undefined. So if you say x equals ln 0, that doesn't exist. So that can't be a solution to this problem. The other way to see it is just to keep in mind like a rough idea of what the graph of e to the x looks like. There is a horizontal asymptote. It's kind of like if you're asking yourself, when does e to the x get down to a height of 0? And the answer is never. It gets really close to 0, but it never quite gets all the way to 0. So the point is, there are two solutions to this problem. Those are the two solutions. Sometimes it looks like there's going to be three solutions, but in fact, there's only two. You could even have a problem where there could be no solutions at all if all of the directions led you to dead ends like this. I'll show you another one similar in some ways. E to the 2x minus e to the x minus 6 equals 0. Now, I think this is the hardest one we've seen so far because it's an exponential equation. X appears in an exponent. But what do we do here? It looks the most similar to the previous problem where we did some factoring. But we don't really have something that we can pull out of all three pieces. Like I can't just I don't think it would help to factor out e to the x from like all three pieces because the 6 here doesn't have an e to the x. Here's my idea. I'm going to think of this as e to the x squared. Okay, all I did was I rewrote the problem in a slightly different perspective. E to the 2x, I'm saying, isn't that the same as e to the x squared? And that way I could think of this as an e to the x, and the middle piece is an e to the x. This almost looks like a polynomial. Okay, I'm going to say this looks like, it's not the same, but maybe it looks a little bit like a squared minus a minus 6 equals 0, right? Like something squared minus something minus 6 equals 0. Maybe I think of it as a squared minus a minus 6 equals 0. So I think it looks like a polynomial. If we actually were in an algebra class and we had a polynomial like this and we wanted to solve for it, we would factor, right? We would say, can this factor? And I guess we would find we could do a minus 3, a plus 2. This would say that a minus 3 is 0 or a plus 2 is 0. And we would continue going on that in that direction. And what I want to tell you here for this exponential equation is that we can do the same kind of thing. We can actually do factoring into two pieces where we get e to the x minus 3 and e to the x plus 2. So the stuff I did to the right was kind of scratch work. Here, I'll label it scratch work. Just kind of explaining my thought process. But yeah, we could factor like this. You could double check that this, if you were to distribute this, it does equal the previous line. It does equal the original problem. What's nice about this is that this means that e to the x minus 3 is 0 or e to the x plus 2 is 0. And we can try to find x now. We've kind of turned it into two simpler exponential equations instead of one big complicated one. So this over here says e to the x equals 3. This over here says e to the x is negative 2. So this says x equals ln 3. I'm going to put a box around that. And that is a solution. But what's going on with this other one? E to the x equals negative 2. A minute ago, didn't I draw a picture of e to the x and I said that, you know, e to the x never gets as low as 0? Well, if it never gets down to 0, it's certainly not going to get all the way down here to negative 2. So there's no solution coming from this direction. You could also say that the reason there's no solution is because ln of negative 2 does not exist. That's another way to think of it. But whichever way you think of it, this problem has one solution, x equals ln 3. Okay, hi there, it's me again. I thought maybe we would take a quick breather, take a quick break. This section has two topics basically: exponential equations, which we just talked about, and logarithmic equations, which we're about to talk about. You saw that when we were solving exponential equations, we did use logs. We sometimes used logs to help us solve those problems. So when we solve logarithmic equations, we are sometimes going to use exponentials. So, they're closely related. And that's where we're at right now. Okay, so take a break if you need to. And let's go ahead and take a look at logarithmic equations. Now, just like with exponential equations, we're going to start off by defining them and then looking at some simple ones. So definition, a logarithmic equation is one in which a log of a variable occurs. All right, so it's not just any equation that has the word log in it. In particular, a log of a variable happens, and the variable is usually going to be called x. So it could be a log with base 10, it could be a log with base e, it could be a log with any base, but the variable is going to be on the inside of it. So for simple equations, we could use the definition of log and exponential form. What I mean is converting back and forth between the log form and the exponential form can help us solve. So for example, let's say we want to solve for x. Log base 2 of x plus 3 equals 4. This is a logarithmic equation. There is a log and the variable is on the inside. It happens to be base 2. If we were to try to rewrite this in terms of exponents, it would be 2 raised to some power, right? Because that's the base. So 2 raised to some power equals something. In fact, it would be 2 raised to this power. 2 raised to the 4 equals x plus 3. Let's write that. 2 raised to the 4 equals x plus 3. That's really what that was saying. This idea that we can convert back and forth between the logarithmic form and the exponential form. From here, we could solve for what x is. First of all, I'll say 2 to the 4 is 2 times 2 times 2 times 2 is 16. So let's do that. And subtract 3 from both sides, and we get x equals 13. Something else I need to tell you here. I didn't put a box around this answer yet. So note, for log equations, we must check our answer in the original problem. And this is not just me being picky and saying I want to see you check your answer. This is actually important because we're going to see some problems where we get an answer and it turns out to be false. So we need to check to see that this 13 really works. I'll show you for this problem that's going to be pretty quick. In the original problem, you put in 13 for x, and it looks like this. And we're saying, does this in fact equal 4? Does everything check out? And yeah, checking is going to be pretty quick because look what this says. It says, does log base 2 of 16 equal 4? Yeah, this is true because 2 to the 4 does equal 16. So I'll just put a check mark next to it. And now that I did this and I see that everything checks out, I'm going to put a box around the answer. X equals 13 is correct. Okay, so I'll show you some more. Just like when we talked about exponential equations, we started with simpler ones and we worked our way up to more complicated ones. And I have another strategy to tell you about here as well. There was a 3-step process before. Well, there's a 3-step process I could tell you about here. It starts by saying isolate the log term on one side of the equation. And we might need to combine log terms. So how would you combine log terms? Like if you had a log term plus another one, you could probably use the laws of logarithms that we talked about. If you have a log plus a log or a log minus a log, if they're the same base, you can use those properties to combine them. Step 2, let's think about what we did earlier for exponential equations. I'm actually going to show you real quick. Earlier, in a 3-step process for solving exponential equations, we isolate on one side. Then it was take log of both sides. So what do you think we're going to do here? We don't want to take the log of both sides again, because we're talking about problems that already have a log in them. You know, taking a log of a log is not going to help. What might help is raise the base to each side of the equation. So the left side will be base raised to the left-hand side equals base raised to the right-hand side. We're getting exponentials involved. And then step 3 is solve for the variable. I'll show you one of these. Let's solve 4 plus 3 log parentheses 2x equals 16. And let's try using this strategy. So it says to isolate the log term on one side of the equation. One good thing is there is only one log in this problem. It's already on one side of the equation. But it has this other stuff. There's a 4, there's a 3. I want to get them out of here. I want to move them away so that the log is isolated without that other stuff. By the way, before I go any further, quick note. I want to point out to you that it would be wrong to say 4 plus 3 is 7. Does everybody see why we can't do that? So 4 plus a 3. It's tempting to just say, oh, I see a 4 plus 3, just make it 7. That would be wrong because order of operations says this 3 is attached to the log. This is like 3 times log, right? We have 3 of these log 2x's. The plus 4 is on the outside. Order of operations says multiplication happens first. So this 3 stays attached to the log. Multiplication happens first, addition happens afterwards. Okay, so that's why it would be wrong to add the 4 plus 3. If there were parentheses kind of encasing them, the 4 plus 3 with parentheses around it, that would be a completely different story. That would be a completely different problem. As it is right now, the 3 stays attached to the log. The 4 is out here floating around by itself. I think we should subtract 4 from both sides. Let's subtract 4 from both sides. That's going to make this 3 log 2x equals 12. Okay, and now let's divide both sides by 3. Divide both sides by 3, you get log 2x equals 4. So just by subtracting something from both sides and dividing something from both sides, we've turned this into an easier looking problem. We've turned it now into what I would call a simple logarithmic equation. We accomplished step 1. We isolated the log term on one side. Step 2 says raise the base to each side of the equation. And this is one of those situations where, again, we could technically use any base we want. You could use base 2, you could use base e, but I think we should use base 10. I think base 10 is going to be the most convenient because this is a log with base 10. Remember, when there's no little number written down here, it's implied that the base is 10. So what's this going to look like? I'm going to do 10 to the left-hand side equals 10 to the right-hand side. The reason why that helps us is because now the left-hand side is a 10 raised to a log base 10, and that simplifies to just 2x. The 10 and the log cancel each other out because they're inverses of each other. Let's continue this up here. This really says 2x equals 10,000, right? Because 10 to the 4 is 10,000. So it says x equals 5,000. And that should be the answer. That probably is the answer, but I'm going to check. I'm going to check in the original problem before I definitively say that's the answer. So in the original problem, this would say 4 plus 3 times log 2 times 5,000. Does that equal 16? And it's okay to subtract 4 from both sides here. In this, this equation that we're checking, I'm going to subtract 4 from both sides. 3, all right, and this is 10,000. Boom. All right, we're checking. Is this true? Log of 10,000. I know what that is because that's a 1 with 4 zeros. So this is like log of 10 to the 4. Right? So this log of 10 to the 4 is 4. So this is saying 3 times 4 equals 12. So yes, everything does check out in the original problem. When I use 5,000, everything looks good. So I'm going to put a box around it and say that is my final answer. Okay, let's look at another one. Move that up. When we talked about exponential equations first, we did some of these same things. Definition, talked about simple ones, talked about a 3-step strategy. What did we say next? We said use algebra when possible. I'm hoping that you think of this as exponentials and logarithms are kind of two different sides of the same coin. They're inverses of each other. So some of the things we say about one of them, we can also say about the other. And yeah, use algebra when possible to help us solve these types of equations. So I'll show you, let's say we had log x minus 2 plus log x plus 1 equals log 4. Everything in this problem seems to be base 10. Do we need to use factoring? Do we need to use, like, what kind of algebra do we need? We'll figure it out as we get there. For right now, I'm thinking, I want to warn you of one potential mistake that some students sometimes do. It would be wrong to just cross out all the logs. You see log, log, log. It's tempting to just cross them all out and say they cancel. That would be wrong. The reason why that would be wrong is because log is not a number. You can cancel numbers like that. If there was like a 5, 5, 5, you know, cancel out the 5s. Log is not a number. It is a function. You can't cancel functions that way. Okay, so we're not doing that. What are we doing then? Well, the three-step process suggested that you try to isolate the log term. Well, we've got a lot of log terms here. I think let's use a property of logs. Let's use a property of logs that says this is log of x minus 2 times x plus 1. Right? That was one of the laws of logarithms. You have a log plus a log, same base. You can combine it with multiplication. From here, I see a couple of different routes that we could go, and to a certain extent, it's kind of a matter of preference. Maybe I'll show you this problem in more than one way. I don't know. Like, one idea that I have is right now I could do 10 to the left-hand side equals 10 to the right-hand side. But I don't know if that would really help, because it looks like the left-hand side would get really messy. Maybe it wouldn't. Maybe it'd be okay. Let's try it. Let's try it. Watch this. I'm just going to write 10s. 10 to this, 10 to this. Let's try it. That's not how I originally did it in my notes. But let's just try this and see what happens. 10 raised to the log base 10 cancels out. 10 raised to the log base 10 cancels out. That leaves us with x minus 2, x plus 1 equals 4. Okay, let's try to work with it from here. Well, wouldn't it be nice if this right-hand side were 0? The right-hand side is 4, so we can't really just, like, say this factor equals 4, this factor equals 4, or anything like that. We need the right-hand side equals 0 to use algebra the way that we like to. How about this? Let's distribute what we have here. X times x plus x minus 2x minus 2. You know what? Let's bring over the 4. I'm saying the 4 being there is getting in the way, so let's bring it over to the other side. Now we can get a 0 on the right. We get x squared minus x minus 6 equals 0. So we expanded, brought over the 4. I'm going to factor. I'm going to factor it now. It seems a little weird that we kind of had something that was already factored. We did a couple of things to it, and now I'm suggesting that we factor it again. But it's different this time because we brought the 4 over. This time it factors into something differently. Right-hand side is going to be 0. So to factor this, we need, well, this would be an x, this would be an x. To factor this, we need two numbers that multiply out to give me negative 6. And when I add them together, they give me negative x. So I'm thinking, you know, maybe a 1 and a 6, maybe a 2 and a 3. One of them should be positive and one of them should be negative in order to get us negative 6. And out of those options, what winds up working is plus 2 minus 3. You multiply them out, they give you negative 6. Add them together, they give you negative 1x. So from here, x plus 2 equals 0, or x minus 3 equals 0. So this says x equals negative 2. This says x equals 3. And those are actual x values, but I'm not putting a box around them yet, because remember, we have to check in the original problem. Let's go all the way up here and check this. Check solutions. We have 2 of them, right? Let's check x equals negative 2. In the original problem, log, when I put negative 2 in, what's it going to look like? In the original problem, negative 2 goes here. Negative 2 minus 2, minus 4, plus log of, put a negative 2 in here, it's going to be negative 1. And we're checking to see, does this equal log 4? Does that check out? Wait a second, we have a major red flag here. Log of negative 4 is undefined. And log of negative 1 is undefined. We said that you can't do log of a negative number. So this is nonsense. This is like saying something undefined plus something undefined equals log 4. No, that doesn't work. So this is not a solution. X equals negative 2 is not a solution. And, you know, I've been having us check our answers to all of these log equations. This is the reason why we check. Because sometimes when you check, you will find out that it is not a solution. Let's check the other one. X equals 3. In the original equation, this would look like log 1 plus log 4. Those are positive numbers, so I feel good about this. Everything's positive that we're taking a log of. Is this true? Does log 1 plus log 4 equal log 4? And yes, that is true. I could see that in 2 different ways. One is we have that property of logs that says we could merge these together to be 1 times 4. Another way that I see this is true is because I remember property that says log 1 is 0. So this thing then is actually just like log 4 equals log 4. Yes. So the solution to this problem, and it is only one solution, x equals 3. So when you're doing these types of problems, it could turn out that for a moment there, it looked like we were going to have 2 solutions, but it turned out that only one of them actually works. What could happen is sometimes in this situation, sometimes both solutions might work. So you could potentially have a problem with 2 solutions, or you could have a problem with no solutions. It could be that none of them work. So you have to check to see if they work in the original equation. By the way, earlier when I said there were like multiple ways to do this problem, when we were here and we did like 10 to the left and 10 to the right, at that step, I was kind of contemplating doing it a different way. I was thinking we have a log on the left, a log on the right, and like, you know, another idea would have been to subtract the log 4 over to the other side, and then use that law of logarithms for quotients, a log minus a log. I was going to do that. It would have all led us to the same place anyway. It would have been fine. So if you see a different way to do it, sometimes that's okay. In fact, let me tell you one other thing. When we were at this step and I did 10 to the left and 10 to the right, technically you could have skipped that little step of 10 to the log, 10 to the log. You could have skipped writing the 10s, and you still could have canceled the log that's on the left and the log that's on the right to get this next line. Now, let me be careful here. At the beginning of the problem, I said it would be wrong to cross out all the logs because log is not a number. We don't just like cancel it as if it were a number. In the second step, however, it would have been okay to cancel the logs because when you get to that step, you have log of something equals log of something. There's no plus, there's no third log, there's just log of something equals log of something. If you're in that situation, it's okay to cancel the logs because log is a one-to-one function, which means it means that these two inputs must be equal to each other. The x minus 2x plus 1 must be equal to the 4. So the point is that there's a couple of different ways of thinking of it that will all kind of get to the same place. Okay, so we spent a while on that problem. Maybe you could say that's the hardest problem we've seen so far in this section. I've got a problem that I'd like you to try of this type. So I am going to write this and then give you a moment to work on it. This one is a log base 4, x plus 1, plus log base 4 of x minus 2 equals log base 4 of 10. So take a couple of minutes and try this. Pause the video if you'd like and see what you come up with, and then we'll talk about it. All right, so I think I'm going to start this in a similar way to that previous problem where I'm going to say there's a plus sign here. So let's merge these together. Let's make this log base 4 of x plus 1, x minus 2 equals log base 4 of 10. Now, we can raise 4 to both sides. 4 to the left, 4 to the right. And when you do that, you're going to cancel out the logs, right? So all you're going to be left with is x plus 1, x minus 2, that's the left side, equals 10. In the previous problem, I said, we got to a step that looked like this, and I said, wouldn't it be nice if the right-hand side were 0? But it's not, it's a 10, so we have to address that. I think what I'll do is expand the left side. And while we're at it, let's bring the 10 over. We could bring the 10 over now, or we could wait one more step. But that 10 has got to go. We want the right side to be 0. Let's clean up the left-hand side now. X squared minus x minus 12 equals 0. And then we look to see, does this factor? If it doesn't factor, then I guess we could consider the quadratic formula. Trying to factor this, we would need an x here, an x here. We would want two numbers, hopefully integers, that when I multiply them out, they give me negative 12. So I'm thinking one of them is plus, one of them is minus, to get a negative number here. And we need to also be able to add them together and get a negative 1 in front of this x. So what kinds of numbers multiply out to give us 12? It could be 1 and 12. It could be 2 and 6. It could be 3 and 4. 3 and 4 seem like a good idea because they're one away from each other, and maybe we'll get this negative 1 here. And in fact, plus 3 minus 4 is the way to go. Multiplies out to negative 12, and they add up to get us this negative x in the middle. This sends us on two different paths. This suggests that x equals negative 3, and this suggests that x equals positive 4. Now we know from past experience that we need to check these before we put a box around them. So let's check solutions. I shouldn't even really be calling them solutions. I should say, let's check the potential solutions that we found. Anyway, you could check them in either order. It's up to you. I'm going to go with -3 first. Okay, so in the original problem, log base 4 of, put in -3, -3 plus 1 plus log base 4, -3. Uh-oh. Looks like this is not going to work, right? This is undefined. As soon as you can see that there's something undefined, it means that this is not a solution. Because we can't have undefined plus something equals something. So that's not a solution. Let's check the other one. Let's check x equals 4. In the original problem, log base 4 of 5 plus log base 4 of 2, does that equal log base 4 of 10? Everything's positive, so that's a good sign. And in fact, you know, log base 4 of 5 by itself, I don't really know what that is. That's kind of a complicated decimal. We can't really find that by hand. However, we don't need to. We can use the law of logarithms that says this is log base 4 of 5 times 2. And yes, that does equal 10. So I'll put a little check mark next to this. It does check out. And now I'll go back and put a big box around this. You know what? Just to be clear, I'm going to cross out the -3 like that. So one solution to this problem, and it was 4. How about we do one more of this type of problem? I'm going through my notes here, finding extra problems, and, you know, the more we can do, the better. So I'll write another problem, and I'd like you to try it. Let's see here. Solve for x. What have I got here? I'm going to give you 2 problems. Log base 2 of x minus 2 minus log base 2 of x equals 1. That's part A. And part B over here, 3 plus... Thinking we didn't do this problem, did we? No, we did one similar to this, but we didn't do this. All right. There's a part A and a part B. I'd suggest that you pause the video, take a couple of minutes, and see if you can do both of these before we talk about them. All right, time to talk about these. Let's start part A over here. So what I'm thinking is this one has a minus sign. You know, in previous problems, we had some plus signs and we merged things together. But you can also merge them together. When there's a minus sign, you use that rule that says this turns into a quotient. So from here, we've got a couple of options. I mean, one way is you could do 2 to the left-hand side equals 2 to the right-hand side. Another way is you could just say, I have log of something equals something, and I know what this means in terms of exponents. The base is 2. It's being raised to the 1. This whole thing means 2 to the 1 equals x minus 2 over x. Two to the 1, of course, is going to simplify to 2. Let's try to get x by itself. Okay, so we need to think of the 2 to the 1 as a 2. Let's multiply both sides by x to get this x out of the denominator. Let's like bring it over here. So we get 2x equals x minus 2. All right, so all I did there was I multiplied both sides by x. We're working on getting x by itself. So how about we subtract x from both sides? That's going to make this x equals negative 2. Not putting a box around it yet because I want to check this in the original problem. You know, does this actually work? Even though we only found one potential solution, we should still check it. So in the original problem, this says log base 2 of negative 4 minus, hold up, this is already undefined. You can tell already, this is already undefined. This is a problem. There's no way the rest of that line can make sense. As soon as you have something undefined, it's not a solution. So in fact, the answer to part A is there is no solution. Because we only found one thing that we thought was going to be a solution, but it doesn't work in the original problem. So this logarithmic equation happens to have no solution. I want to warn you about one thing. I'm thinking about the problems we've done, and it seems like whenever we get a negative value of x, it seems like it doesn't work. So there's a subtle thing that I want to point out here. Okay? It is possible for a logarithmic equation to have a negative answer. I don't think it's happened in any of the examples that we've seen today. We've gotten answers like x equals 3, x equals 4. I'm telling you now, it is possible to have a negative answer. Because what if instead of, like, if this wasn't an x minus 2, what if this was like a 2 minus x? Something like that could happen where you would potentially be able to plug in a negative x value but still have this part be positive. Does that make sense? All that really matters is whether this part is positive or negative. This part, the x value, you don't automatically rule it out just because it's negative. You rule it out because this happened. Okay? Let's work on part B. Hopefully what you did on part B was, I would subtract the 3 from both sides. Let's just get rid of that. So 4 log 2x, subtract 3 from both sides, you get 12. I think this is going to look very similar to one that we did a little bit earlier. Divide both sides by 4, you get a 3. And this means, when I say the phrase this means, I guess I'm converting from log form to exponential form. I'm thinking I have a base of 10, 10 to the 3 equals 2x. So either think of it that way, or raise both sides. Do 10 to the left equals 10 to the right. That will get you here also. 10 to the 3 is 1,000. So 1,000 equals 2x. And this suggests that x equals 500, which we are going to check. In the original problem, does 500 work out? So 3 plus 4 times log of... When I put 500 in, this is going to be 1,000. So does this equal 15? Three plus 4 times log of 1,000. We know what that is, right? Because this is a base of 10. So 10 to what power is 1,000? 10 to what power is 1,000? 3. It's a question mark there. So this is 3 plus 12. Does equal 15. Yes, that does check out. So now I'm going to go back and put a big box around the x equals 500. That is the solution. All right, so I'm glad we did those extra problems. It's always good to see more examples. Now, there's one more thing for this section. I'd like to show you an application of this. And when I say this, we've been talking about both exponential and logarithmic equations. What application can I show you? Well, one application that we've seen so far of exponentials was interest. So let's revisit interest and see if there's a type of problem that we can do that's brand new to us for this section. So first of all, recall we have two different interest formulas. This is for interest compounded n times per year. And a of t equals p e to the rt. This is for interest compounded continuously. And you use the formula that's appropriate to the problem. If the problem says it's compounded continuously, use the second formula. If it says it's compounded monthly or annually or daily or weekly, whatever, you use the first formula. So here's a word problem, and we'll do this one together. I'll kind of talk us through it. I think because this is going to be a dollars and cents type of problem, we might use a calculator at some point to help us out with it. Even though we've been avoiding calculators lately, sometimes for dollars and cents, we're going to use it. All right, if $10,000 is invested at 5% interest, how long does it take for the money to double if interest is compounded? Dot, dot, dot. There's going to be a part A and a part B. Part A, monthly. Part B, continuously. Now, I said that I was going to talk us through this problem, but I'm just going to give you a minute in case you're writing that down. So this is a different type of interest problem, because most of the interest problems we've seen, they generally have been asking, like, how much money will there be after 3 years or something. This one, instead of asking how much money will there be, it's kind of telling us how much money there will be. It'll be double, right? So we know how much money there will be, but the question is, when will this happen? Okay. Let's work on part A. Let's move this up. So part A, if $10,000 is going to double, doesn't that mean there's going to be $20,000? So $20,000, and I'm going to put this into the first interest formula because it said that interest is compounded monthly. So 20,000 equals the principal times 1 plus the interest rate divided by n is the number of times interest is compounded per year, which is 12, raised to the nt. It's going to be raised to the 12t. Our job is to solve for t. If we can solve for t, then we've answered the question. Everything else was given to us. The amounts of money, the interest rate, the 12. T is the only unknown. So this is an exponential equation, isn't it? It's an equation in which the variable appears in an exponent. And throughout this whole video lesson, the variable has typically been called x. And I told you that the variable will usually be called x, but in this one it's called t because it represents time. So, the first thing that I did for this problem is I said there's a 20,000 and a 10,000. Let's divide both sides by 10,000. Also, I decided to use a calculator to simplify the part that's in parentheses. Be careful about rounding this off too much. I got 1.00416 repeating. So if I have to use that in one of the upcoming steps, I'm going to use a lot of digits. So this is a little exponential equation. We want to get t by itself. Let's see here. The base is 1.0041. Like, look at this base. That's pretty messy, right? We could do log with that base of both sides. But remember at the beginning of this lesson, I told you that when you do log of both sides, technically you could use whatever base you want. I even showed you that on a couple of problems. I said if you want to use base 10 or base e or whatever, you can do that. I don't particularly want to use I don't want to use base 1.00416 repeating. I think that's going to be messy. I'm going to do a log of base 10 of both sides. Just base 10, because that's going to be easy to work with. When it's base 10, you just write log. This is going to be okay. We could still work with this, because remember, we have that property that says when you have an exponent in a logarithm, you can pull that out. So on the right side here, I'm going to pull out the 12t. Log 1.00416 repeating, and the left-hand side is still log 2. So I could solve for t. T is in the middle of this whole mess, but let's just divide both sides by something, and this will work out. So log 2 divided by 12 log 1.00416. This answer might look different if you did this with a different base, but I chose base 10. And that is a number, right? That's a messy looking number. And I found with a calculator, this is approximately equal to 13.89. And I'll say that it's 13.89 years because it represents a length of time. I kind of feel like part B, I was going to say E because we're going to use the number E. I kind of think part B is going to be easier. I kind of think it's going to be easier. So how about this? Let me give us some space here. I'm going to ask you to try part B on your own. So which way should I move the paper then? I think what I'll do is I'll cover up what we just did. I mean, this is a video, so you can always pause it or rewind if you need to. I am going to ask you to try part B for a minute. Go ahead and pause it if you'd like, and then I'll talk about it. So the reason why I said that I thought part B might work out easier is because we're using the second formula now. We're using the simpler looking formula for interest. So again, 20,000 is the amount that we're after. 10,000 is the principal. But now we have e to the 0.05t, and we would like to solve for t. So I feel like this is a simpler formula to work with. It wasn't really an option for part A. We had to use the complicated formula for part A. All right, let's divide both sides by 10,000. Let's move the first sheet away. So what do we want to do here? We could get some kind of logarithm involved, and we get to choose what base we use. We could use base 10. I think for this problem, I would use base e, because e raised to the, e raised to something. When you do a log of base e of both sides, it's ln. So ln of the left equals ln of the right. And we're doing that because the right-hand side simplifies to this. Can we figure out what t is? T is... Do we want to say ln2 divided by 0.05? I guess we could, but I think what would be nicer is I notice that 0.05 is 1/20th. So this is going to be 20 ln2. And I found this also as a decimal on a calculator is about 13.86 years. Which makes sense, because I was expecting the answers to part A and B. I was expecting the answers to be very close to each other. Technically, having the interest compounded continuously should get you more money faster. So it makes sense that this is slightly less time for part B. Slightly fewer years. So what we just did in this problem, this was a word problem. It was an application of, I guess you could say this is a real-life application of exponential equations and logarithms. And the reason that I have this problem here towards the end of the section is because this is going to help lead us into the next section, which is also going to be word problems, and it's also going to be applications. And I think in that section, we're going to look at some other applications. But I want to say one thing before I move on, just because I have always found this interesting. In this problem, it was originally said, I'll just show you it here. It was originally said that we invested $10,000, right? What I find interesting is what would happen if we had this exact same problem, but instead of starting with a principal of 10,000, what if we started with a different amount? What if we started with 12,000? How would that affect the answer? So let's imagine that this was a 12,000. I'm not going to rewrite the whole problem, but imagine this was 12,000. And let's just focus on part B, okay? This 10,000 would be a 12,000. The question is still asking how long would it take for the money to double. So instead of 20,000, I would have a 24,000. So I would have 24,000 equals 12,000 times this other stuff. What would I do next? I would divide both sides by 12,000 and I would get a 2 here. So the rest of the problem would be exactly the same, and we would get exactly the same answer. So I find it interesting that the principal, the 10,000, it doesn't really matter. It cancels out and is going to give us a 2 here. If you did the same problem and you started with an investment of 7,213, you'd still get the same answer. If the question is, how long will it take for your money to double? That's why this is a 2. It's a 2 because we want the money to double. And that's why the answer has ln2 in the answer. That's kind of cool. So I guess if a problem were to ask us about, like, how long does it take for the money to triple, I would expect a 3 to show up. Anyway, I just think it's interesting that the principal doesn't matter. No matter how much you invest, it's going to take the same amount of time to double. It's kind of cool. All right, so that was our section on exponential and logarithmic equations. And we finished with that word problem about interest, which is, word problems are basically the way we get some real-life applications showing up. The next section is going to have other types of word problems. We might look at some things like population growth, other things that exponential functions and logarithmic functions are used for, because they are used for more than just interest. But yeah, that's it for right now. So have a good one, and I'll see you next time.